Welcome to WikiPodcast. This is a deep dive into something absolutely fundamental to our world, yet, well, often invisible: electricity.
It really is. It's that force that kind of follows a path all the way from tiny subatomic particles right up to massive thunderstorms. And it's all driven by basically the motion of matter that has an electric charge.
And that motion, that fundamental force, it's literally the foundation of modern industrial society, isn't it?
Absolutely. Can't imagine life without it.
So our mission today is to, dig into this, pull out the really key ideas, the fascinating bits, and make this whole complex thing feel a bit clearer, maybe even electric for you.
Sounds good. Where should we start?
Okay, let's unpack this right at the very beginning.
Hmm.
Everything seems to start with electric charge.
Yeah.
What is that, fundamentally?
Right. So think of it like mass. It's just a basic property of matter. It's carried by subatomic particles. The main ones we talk about are electrons that get a negative charge, and protons, which have a positive charge. And there's this idea of an elementary charge. That's like the smallest possible packet of charge you can get. It's the charge on one proton or the negative of it on one electron. All other charges are just multiples of that.
Okay, so tiny building blocks of charge. And what happens when these charged particles, meet each other?
Yeah, that's where the action is. It's pretty simple, actually. Like charges push each other away, they repel, and opposite charges pull together, they attract. This force, the one between charges just sitting there, we call it the electrostatic force, and it follows Coulomb's law, which, interestingly, is an inverse square law, just like gravity, weaker with distance squared.
And this is the bit that always gets me. It's so much stronger than gravity, right?
Oh, unbelievably stronger. It's staggering. The electromagnetic force between, say, two electrons is something like 10 to the power of 42 times stronger than gravity between them.
10 to the... Wow.
Yeah, it means even tiny imbalances in charge just completely overwhelm gravity at the small scale. It's why magnets work, why atoms stick together, why chemistry happens, why you don't fall through the floor. It's all electromagnetism stemming from charge.
That really puts it in perspective. Okay, and charge can move around, obviously.
Right, and the key idea here is charge conservation. The total amount of charge in like an isolated system always stays the same. You can move it, transfer it, but you don't create or destroy net charge. Static electricity is a perfect example of transfer. You rub two different things together, maybe a balloon in your jumper.
Yeah.
Electrons jump from one to the other. That creates a temporary imbalance of charge. That's your static cling, or that little shock you get from a doorknob. People used things like gold leaf electroscopes way back when just to detect that imbalance.
Right, the little leaves pushing apart. So charge is the property. Static is like charge hanging out.
The imbalance, yeah.
And when that charge moves, that's current.
Exactly. Electric current is just the flow, the movement of electric charge. We measure it in amperes or amps, and it flows easily through some materials, conductors like copper wire, but gets blocked by others. Insulators like rubber or plastic.
Now, you mentioned something a bit weird about the direction of current, conventional versus electron flow.
Yes. That's a historical quirk, really.
Oh, wow.
So when they first started figuring this stuff out, long before they knew about electrons, they just assumed it was positive charge that moved. So conventional current is defined as the direction positive charge would flow, from high potential to low potential, like water flowing downhill.
Okay.
But in most everyday circuits, like wires, it's actually the negatively charged electrons doing the moving. And because they're negative, they drift the opposite way to the conventional current.
So the map is kind of backwards, but it still works for navigation.
That's a great analogy, yeah. For analyzing circuits, the convention works perfectly fine, so we stick with it. Doesn't matter if it's electrons going left or positive charges going right, the math comes out the same. And sometimes current is positive charges moving, like ions in a solution.
And the speed thing, the electrons move slowly, but the light comes on instantly. How does that work?
Right, that's another cool point. The individual electrons in a wire, they actually drift incredibly slowly.
Right.
Like millimeters per second. Really slow.
Seriously, millimeters.
Yeah, the drift velocity is tiny, but the signal that tells them to move, the electric field that pushes them, that travels through the wire at nearly the speed of light. So you flip the switch, the field spreads almost instantly, and all the electrons already in the wire start drifting pretty much simultaneously. That's why the light comes on right away. It's not one electron racing from the switch to the bulb.
Okay, that makes way more sense. It's like a domino effect, but super fast.
Kinda, yeah. More like pushing a long, rigid rod, push one end, the other end moves instantly.
Got it. And this moving charge, this current, it does other things too, right? Historically.
Oh, yeah. People noticed early on, Current could break down water, that's electrolysis. It makes things hot when it flows through them. Joule heating, like in a toaster. And the really big one, Arsted's discovery in 1820. He saw, kind of by accident, that a current-carrying wire moved a compass needle. That showed electric current creates a magnetic field. That was huge, the first solid link between electricity and magnetism.
And sparks, arcs, they mess with radio signals.
Right, that electromagnetic interference, or EMI. It's basically the rapid change in current and fields during an arc, creating radio waves that interfere with other signals, a practical consequence of that electricity-magnetism link.
Okay, and just quickly, the two main flavors of current, DC and AC.
Yep. DC is direct current. Flows steadily in one direction. Think batteries, the power inside your phone or laptop. AC is alternating current. It reverses direction back and forth, usually in a smooth sine wave pattern. That's what comes out of the wall sockets. AC is really good for transmitting power over long distances, even though the electrons themselves are just sort of wiggling back and forth.
Willing electrons powering my house. Okay, so let's shift gears slightly. You mentioned fields, the electric field. What's the concept there?
Okay, so if charge is the source, the electric field is like its area of influence in the space around it. Any charge creates this field. And if you put another charge into that field, it feels a force. It's a bit like gravity. You know, a planet creates a gravitational field, but the electric field is different because it can push or pull depending on whether the charges are positive or negative.
And the strength of that field. It's about the force.
Exactly. The field strength at any point is defined as the force that a small positive test charge would feel, if you put it right there, divided by the amount of test charge. And it's a vector and has direction as well as strength. Points away from positive charges towards negative ones.
Faraday helped us picture these fields with lines, right?
Yeah, his field lines. They're imaginary, but super useful. They show the direction a positive charge would move. They start on positive charges and on negative ones. They never cross each other. And where they're packed closer together, the field is stronger. And a neat trick. They always hit the surface of a conductor at a right angle. Because if they didn't, charge would move along the surface until they did.
Which kind of explains the Faraday cage?
Precisely. If you have a conducting enclosure, like a metal box or even your car body, any external electric field makes the charges in the conductor rearrange themselves. They move until they create their own field inside that perfectly cancels out the external one. So inside, zero field. You're shielded.
That's why you're safer in a car during a thunderstorm. And speaking of thunderstorms, lightning, that's just a massive electric field doing its thing, isn't it?
It's nature's spectacular electrical show. What happens is charge separates inside the clouds or between the cloud and the ground. This builds up a huge electric field. Air is normally an insulator. It doesn't conduct electricity well. But there's a limit. It's dielectric strength. Something like 30,000 volts per centimeter, though it's easier to break down over long distances. When the field gets stronger than that limit, the air basically breaks down, becomes ionized, turns into a conducting plasma channel, and zap. That's lightning. We're talking potential differences of maybe 100 million volts or even more.
Oh, and lightning rods. They work because the field is stronger near sharp points.
Yep, electric fields get really concentrated around sharp points, so the lightning rod encourages the discharge to happen there, providing a safe path to ground rather than through the building itself.
Okay, from fields to potential or voltage. How are they related?
They're closely linked. Electric potential is about the energy. Specifically, the potential energy a charge would have due to the electric field at a certain point. But what's usually more practical is the difference in potential between 2 points. That's voltage. It tells you how much energy is gained or lost per unit of charge when you move it between those 2 points. Measured in volts, which are joules per coulomb.
I liked the gravity analogy for this too.
It works well. Think of height in gravity. Higher up means more gravitational potential energy. Voltage is like the electrical height. Positive charges naturally want to fall from high voltage to low voltage, releasing energy. Negative charges go the other way. And those lines of equal potential, equipotentials, they're like contour lines on a topographic map, always perpendicular to the field lines, the direction of steepest descent.
And we usually need a 0 point, like sea level for height.
Right. For electrical circuits, we often define the earth or ground as being at 0 volts, our reference point.
Okay, let's loop back to that huge discovery by Ørsted, current-making magnetism.
Yeah, that really kicked things off. Ampere quickly followed up and showed that since currents make magnetic fields, 2 wires carrying current will actually push or pull on each other. Attract if the currents are in the same direction, repel if they're opposite. That force is actually how we define the amp.
And that force is the key to electric motors, right?
Absolutely. Faraday built on this. He showed that if you put a wire carrying current inside a magnetic field, the wire feels a force. That's the principle of the electric motor, turning electrical energy into motion. Powers almost everything that spins or moves electrically.
But Faraday wasn't done. He found the flip side, too. Induction.
Electromagnetic induction, yeah. Maybe even more important for how we live today. He discovered that if you change the magnetic field going through a loop of wire, or move a wire through a magnetic field, you create a voltage in that wire. Magnetism can generate electricity.
That's the basis for generators.
Pretty much all large-scale generation, yes. His first generator was just a spinning copper disc. Not very efficient, but it proved the concept was possible.
Then Maxwell tied it all together.
James Clerk Maxwell, yeah.
Mm-hmm.
His equations in the 1860s were just revolutionary. They unified electricity and magnetism completely, showed they were two sides of the same coin, electromagnetism. He predicted that these changing electric and magnetic fields would travel as waves, calculated their speed, and boom, it was the speed of light. He proved light is an electromagnetic wave.
Yeah.
Mind-blowing stuff.
Truly. And all these amazing principles come together in, well, circuits.
Right. An electric circuit is just a path, an interconnection of components that lets charge flow around, usually to do something useful like light a bulb or run a computer.
And the basic building blocks, resistors, capacitors.
Yeah, the key passive components. Resistors resist the flow of current, turning electrical energy into heat. That's Ohm's law, VIR, relating voltage, current, and resistance. Capacitors store energy in an electric field. They build up charge. They block steady DC current once they're charged up, but let AC current pass through, in a sense. And inductors, usually coils of wire, store energy in a magnetic field. They tend to resist changes in current, so they behave very differently depending on whether it's AC or DC.
Okay, so bringing it all together, charge, current, fields, induction. How does this actually run the modern world? And where else does electricity pop up?
Well, generating it on a large scale mostly still comes down to Faraday's induction. We spin turbines using steam from burning fossil fuels or nuclear reactions, or using wind or water power, and those turbines spin generators, which are basically magnets and coils of wire. Solar panels are the main exception, using the photovoltaic effect to turn sunlight directly into electricity.
And we're using more and more of it.
Oh, massively. Global demand keeps rising, especially in developing economies. And that rise, linked to fossil fuels, is really pushing the switch towards renewables like wind and solar.
But getting the power from, say, a wind farm to our homes isn't simple.
No, and the invention that made the modern grid possible was the transformer back in the late 1800s. It lets us step voltage way up for long-distance transmission. High voltage means lower current for the same power, which drastically cuts down energy loss in the wires. Then we step it back down to your homes and businesses for safe use.
But storing it is still tricky, especially with solar and wind not being constant.
That's the big challenge now, grid-scale energy storage. How do you store huge amounts of electricity efficiently and affordably when the sun isn't shining or the wind isn't blowing? Batteries are getting better, pumped hydro storage helps, but it's a major focus of research.
And the uses are just everywhere.
Everywhere. Early electric lights replacing dangerous gas lamps. Heating and cooling, although simple electric heating can be inefficient. Things like heat pumps are much better. Electric motors, obviously, in industry, appliances, now cars and trains. Telecommunications started with the telegraph, now global instant communication. And the whole digital revolution, transistors, integrated circuits, it's all built on controlling tiny electric currents.
It feels so man-made, but you're saying it's deeply natural, too.
Absolutely fundamental to nature. We talked about forces between atoms. The Earth has a magnetic field because of electric currents in its core. Some crystals, like quartz, show piezoelectricity. Squeeze them, you get a voltage. Apply voltage, they deform slightly.
And electricity in living things, that's wild.
It's incredible. Some fish, like sharks, can sense the weak electric fields produced by other animals' muscles' electroreception. Others, like electric eels, can generate powerful shocks for hunting or defense using specialized cells called electrocytes. But the most amazing part, all animals, including us, rely on electricity. Our nerves and muscles work by sending tiny electrical signals, voltage pulses, called action potentials. It's how information travels, how muscles contract. It's all based on carefully controlling the flow of charged ions across cell membranes.
So when you get a shock, it's messing with that system.
Exactly. It's artificially stimulating those nerves and muscles. That's why even a small current can cause involuntary muscle contractions or interfere with your heart's rhythm.
Which brings us back to the dangers.
Yeah, the main hazard is current flowing through the body. You can feel Just a tiny amount, a few milliamps. Higher currents are dangerous muscle spasms, heart fibrillation, nasty burns from the heating effect. And because you can't see it, it's an invisible hazard. It was even used grimly for executions historically, though that's very rare now.
Thinking about how we perceive it culturally, it feels like it's changed over time.
Oh, definitely. At first, it was pure mystery, maybe even magic. Think about those early experiments with static electricity, sparks jumping. It must have seemed otherworldly, fed into stories like Frankenstein, animating life with this strange force.
Then it became the engine of industry.
Right. Symbol of power, progress. The engineers, the electricians, they were like modern wizards taming this force, celebrated in art and literature of the time.
And now it's just there until it isn't.
Exactly. It's become so essential, so ubiquitous, that we mostly only notice it when the power goes out. A blackout is a big deal. And the people who keep it flowing, the line workers out in storms, they gain this sort of quiet heroism, like in that song Wichita Lineman. It's gone from magic to mundane necessity almost.
Yeah.
There's that famous story, maybe not true, about Faraday showing his experiments to Gladstone, the politician. Gladstone supposedly asked, "But what use is it?" And Faraday is said to have replied, "Why, sir, there's every probability that you will soon be able to tax it." Even then, the potential was clear, at least to some.
So quite a journey, from the tiniest charges pushing and pulling
To their flow, creating currents and magnetic fields, the whole dance of electromagnetism.
from harness to build generators, motors, grids, lighting everything up, connecting everyone.
Powering computers, phones, all of modern tech.
While also being this fundamental force in nature, from lightning strikes.
Right down to the electrical signals firing in our own nerves and brains.
It really is incredible how this invisible force shapes, well, everything. So here's something to ponder based on all this. Given that our own bodies run on electrical pulses and nature produces these massive electrical events like lightning, how does understanding this fundamental force change how we see both the universe around us and maybe even ourselves?
Thanks for listening. Write us your opinion in the comments on what natural electrical phenomena you find most fascinating. Subscribe to the channel to help more listeners reach our episodes. Thank you and have an amazing day.